Hello everyone. Now in basic electrical engineering, there's a topic called resonance. This resonance is nothing but it is defined as a phenomena or process in which the output is maximum for a constant input. Means amplitude. Means here you'll give different inputs. Then you'll get different outputs. At a particular input, if the output is maximum, then that condition is known as resonance. Here, take an RLC series circuit, means resistor, inductor and capacitor are connected in series connection, and an AC voltage. Now here, to get output maximum, here output is current because you'll apply voltage and current will flow. So input is voltage and output is current. So here for resonant condition, the output means current should be maximum, right? And then here I is equals to V by Z. Means here the impedance means the resistance of AC or impedance should be less. Then only the current will be maximum. So to make impedance less, Z is equals to R plus J into XL minus XC. We can also write as mod Z is equals to square root of R square plus XL minus XC whole square. To make this minimum, the first condition what we can do is make this as 0. If this is 0, Z will be R. Minimum value is R. So, to get maximum output or maximum current means in resonant condition XL minus XC will be 0. Imaginary part will be 0. Then impedance Z will be minimum. If Z is minimum, then current will be maximum, means output is maximum. Then this condition is known as resonance. So XL minus XC is 0. XL is omega L minus XC is 1 by omega C is 0. Now omega square is equal to 1 by LC. Omega is equal to 1 by root LC. Omega is also written as 2 pi F. F is equal to 1 by 2 pi root LC. This is known as resonant frequency. So at this frequency, XL minus XC is 0. Means when XL minus XC is 0, impedance is minimum. When impedance is minimum, current is maximum. Means output is maximum. Means it is resonant condition. That's why this frequency is known as resonant frequency. So we can define resonant frequency as the frequency at which current is maximum. Why? If impedance is minimum, then current is maximum. And or you can also define resonant frequency as the frequency at which XL is equals to XC. At this frequency only the XL is equals to XC, right? If XL is equals to XC, then it will become 0, impedance will be minimum, current is maximum. Yes. Or if the frequency at which the applied voltage and current are in phase. Why this definition is, here you will get Z is equals to R, right? Refer resistor, the voltage and current move in same line, means the phase difference is 0. So both are in phase. That's why the frequency at which the applied voltage and current are in phase means phase difference is 0, because at resonant frequency means at resonant condition here impedance is equal to R, it acts as a resistor. That's why. Or you can also define as the frequency at which power factor is unity. Here as I said, V I for R for resistor, because here Z is equals to R, right, at a resonant condition. So for resistor, voltage and current move in same line, means phase angle difference is 0, means theta is 0. What is power factor? Cosine of angle between voltage and current. Angle between voltage and current is 0. So theta is 0, cos 0 is 1. So here the frequency at which the power factor is unity. And the variation of XL, XC, XL minus XC impedance current with respect to omega. So XL omega, we all know that XL is equals to omega L. So it is Y is equals to mx Y is equals to mx line. XC is and omega. Here XC is equals to 1 by omega C. So it is exponential in way. It means here if omega is minimum, XC is maximum. Omega is minimum, XC is maximum. In that way. Now XL and XC combination. We all know that for omega XL XC, XL omega will be like this. XC omega will be like this because for negative. Now if you combine both as XL minus XC, then it starts from here. And from here it will be straight line above x-axis because it acts as inductor. So inductive dominance, here it is capacitive dominance. So this is XL minus XC curve, this combination. You can write like this. Now here it is XL minus XC, here it is XC minus XL. And here at this point, XL is equals to XC, right? Means it is resonant condition, right? So here XL is equals to XC means XL minus XC is 0. So it is 0 means here it is known as FR, resonant frequency. I already said here. XL minus XC is 0 means this frequency is known as resonant frequency. So at this condition, if XL is equals to XC, then frequency is known as resonant frequency. So if the characteristics, in the characteristics, the frequency at which XL and XC are equal and opposite in direction, XL is equals to XC, then the frequency is known as resonant frequency. FR is equal to 1 by 2 pi root LC. Here the reactance is X is 0, imaginary part is 0. Because Z is equals to R plus J of XL minus XC. As I already said, this part is 0. Means reactance X is 0. Means imaginary part is 0 in impedance in resonant condition. Now, here below the FR, the circuit nature is capacitive. Here below FR, XC will dominate, right? The below resonant condition, it acts as a capacitive in nature, capacitive dominance. Above resonant condition, it acts as an inductive dominance. Means the dominance of inductive nature is more because XL. And at the resonant condition, it acts as a resistor because as here XL is equals to XC, XL minus XC is 0, no inductive nature, no capacitive nature at resonant condition, it acts as a resistor. That's why at resonant frequency the circuit nature is resistive. At resonance, pure realistic part is observed as imaginary is 0. As I already said, at resonant condition R plus J times of XL minus XC, as this part is 0, imaginary part is 0, you will observe only real part. So Z is equal to square root of R plus R square plus XL minus XC whole square. XL as omega L, XC as 1 by omega C. At omega is 0, if this is 0, if denominator is 0, it 1 by 0, it will be infinite. So Z will be infinite. If omega is infinite, then also Z will be infinite. At omega is equals to 1 by root LC, means at resonant condition which we have done already, at this omega is equal to 1 by root LC, Z is equals to R. So, always Z is not equal to 0, means impedance is not equal to 0. Some impedance will be there, even at maximum condition also. That's why this impedance is not 0, means that resistance which opposes that AC current flow is not at all 0. Some of the restriction of the current will be there. Here, when omega is 0, Z is infinite. Slowly it will decrease. At omega is equal to 1 by root LC, at resonant condition, that Z impedance is minimum, when Z is R. Now when you increase the omega to infinity, then Z will go to infinity. So, here below FR, I already said it acts as capacitive in nature. Because see, below FR means at omega is 0, 0 minus 1 by 0 is infinity, means XC will be infinity, right? Means more capacitive nature. That's why it acts as capacitive. After FR means when omega tends to infinity, means here infinity into L minus 1 by infinity is 0. This will be 0. Means XC is 0. But XL is infinity. So as XL is infinity, from here inductive nature will dominate more because XL is more. That's why. We all know that I is equals to V by Z. So if Z is increased, I is decreased. So here Z is more, it is opposite. See. So At this condition, at a resonant condition, this is capacitive in nature, this is inductive in nature, and this is resistive in nature. So, maximum current is observed here. Where maximum current is observed, then that frequency is known as resonant frequency, when resonant condition. Next, since series circuit allowing the current and is named as acceptor circuit because output current is maximum. So here in resonant condition, the output current is maximum, right? At resonant FR, at resonant frequency. So here the current will be maximum in series connection. So it is named as an acceptor circuit. It can accept more current. So we have drawn impedance graph, current graph. Now we are going to draw power graph. We all know that P is equals to I square R. For current it is like this. For current it is like this, omega I. For power also it will be like the same, but little bit higher because I square, but same shape. So here omega R, at resonant condition power is maximum, at capacitive condition, here it is inductive condition. And here if you draw a line, and when you draw a line, here at two different frequencies the power will be same. Otherwise for other condition the power won't be same actually. So here this is F1 and F2 are known as half power frequencies. At Pmax by 2 this is Pmax. This is Pmax by 2. How is, I will tell. Half power frequency means these frequencies are defined as the frequencies at which the power in the circuit is 50% of maximum value. So half power frequency means F1 and F2. Why it is named as half power frequency? The reason is at this frequency the power is maximum, half of maximum. At this frequency the power is half of maximum. So that's why it is half power frequency. So P is P max by 2. P max can be written as I square max into R by 2. This we can write as I max by root 2 whole square. So the current will be I max by root 2, right? So the frequency at which the current in the circuit becomes 1 by root 2 times of maximum current. So see here, at this frequency the current is I max by root 2. At this frequency current is I max by root 2. So 1 by root 2 is 0.707, that's why when the current will be 70.7% of maximum current. When power is half, 50% of maximum power, then that frequency is known as a half power frequency, or you can also define as the frequency at which the current will be 1 by root 2 times of maximum or 70.7% of maximum, then it is half power frequency. Or here I is I max by root 2, 1 by root 2 of I max. I max can be written as 1 by root 2 of V by R. Why R? Actually it is V by Z, but Z we can write as R because I max means resonant condition, right? At resonant condition it acts as resistive in nature, right? Then Z will be R, right? Because Z is equals to R plus J into XL minus XC. At resonant condition this will be 0. So Z is R. So I max will be V by R, 1 by root 2 times of V by R. I is V by Z, V get cancelled, Z is equals to root 2R. So same, at these two frequencies, the frequencies at which the impedance become root 2 times of resistance, or impedance become root 2 times of impedance at resonance. Here R means impedance, Z is equals to R, right? This is Z only, but at resonant condition. So we can also name this R as impedance at resonance. The frequencies at which the impedance become root 2 times with or 141.4% of impedance at resonance. Then it is named as half power frequency. Next, bandwidth. Bandwidth is nothing but it is defined as the range of frequencies band at which the current limit is 1 by root 2 times of maximum, 1 by root 2 times of maximum, or power limit is 50% of maximum, power limit is 50% of maximum, or impedance limit is 141.4% of impedance at resonance. Means bandwidth means, here see, these two are half power frequencies. In between all frequencies are known as bandwidth. Here also, actually all are same. So in between two half power frequencies, all other frequencies are known as bandwidth. Once again, the frequencies in between f1 and f2 means half power frequencies. Then all those frequencies are termed as bandwidth. So it is f2 minus f1, right? Means omega 2 minus omega 1, right? When delta f, so higher, so this is higher cutoff frequency and this is lower cutoff frequency. So mod z is equals to square root of r square plus xl minus xe whole square. As we all know, z is equals to root 2r because at resonant frequency z is root 2r, right? Root 2r, r square plus xl minus xe whole square is equals to 2r square. So xl minus, here xl is omega l and x is 1 by omega c square, squaring on both sides. Now 2r square, here 2r square minus r square is r square. Omega l minus 1 by omega c is plus or minus r. As resistance is always positive, we will take plus r. Here it is omega square lc minus 1. This will come here minus omega rc equal to 0. It is looking like a quadratic equation with variable omega. Now take minus b plus or minus under root b square minus 4ac by 2a. Then you will get omega 1 and omega 2 because plus or minus. That plus will be omega 1, minus will be omega 2, two frequencies. Here f1 and f2, right? Omega 1 and omega 2. For half power frequencies in that way. You will get 2. Omega 1 and omega 2. Another way to obtain half power frequencies are omega 2l minus 1 by omega 2c is r. Omega 1l minus 1 by omega 1c is equal to minus r. How we got this is from this formula. Omega l minus 1 by omega c is plus or minus r, right? So here in one case you substitute omega 1, other case you substitute omega 2. Then add both. Omega 1 plus omega 2l, this if you add, r minus r will be 0. Here take omega 1 plus omega 2 as common. This will be 0 obviously. And L minus 1 by omega 1 omega 2 into C is equal to 0. L is 1 by omega 1 omega 2 into C. Omega 1 omega 2 is equals to 1 by LC. Here, to find what is 1 by LC, here XL minus X is 0, right? Because we are calculating at resonant condition. At resonance, XL minus X is 0. XL is omega L. X is 1 by omega C. Here, when you can simplify it, omega square is 1 by LC. So, this is omega square. So, omega r square actually, because it is resonant condition. Omega 1 omega 2 is equals to omega r square. Omega r is square root of omega 1 omega 2. Omega r can be written as 2 pi fr. Fr is resonant frequency. Omega 1 is 2 pi f1. Omega 2 is 2 pi f2. Fr is square root of f1 f2. This is one. And next is you subtract it. When you subtract it, take omega 2 minus omega 1 as common. L plus 1 by C omega 1 omega 2 is equals to 2r. Here 1 by omega 1 omega 2. Here omega 1 omega 2 is 1 by LC, right? So omega 1 omega 2 is 1 by LC. Then omega 1 omega 2 will be 1 by omega 1 omega 2 will be LC. So 1 by omega 1 omega 2 will be LC. C get cancelled. L plus L will be 2L, 2R, 2 get cancelled. Omega 2 minus omega 1 is R by L. F2 minus F1 is R by 2 pi L. So this is omega 2 minus omega 1 means F2 minus F1 means this is delta F, bandwidth, all frequencies in between F1 and F2, all frequencies in between half power frequencies F1 and F2, which is R by 2 pi L. Next is quality factor. Quality factor is nothing but this plays an important role to select a particular inductor or capacitor for resonance phenomenon. Here in resonant condition means our circuit should contain R, L, C, right? Inductor, capacitor and resistance. In that Ah, so you need to select an inductor and capacitor to get resonant frequency means maximum current. For that, this quality factor will check. Quality factor means it will check the quality of the inductor and capacitor so that you can get maximum current. Means maximum current means maximum output means resonant condition. So you can also say that the energy efficiency of energy storing element means inductor and capacitor, will be decided based on quality factor. So based on quality factor, you can check which inductor you need to select and which capacitor you need to select. So you can define quality factor as ratio of the voltage across the inductor to the applied voltage at resonance. For RL, if it has RC, then ratio of the voltage across capacitor to the voltage applied at resonance. At resonance means at resistance. So VL, voltage across inductor to the voltage across at resonance means at resistor. For C means VC by V. VL means I max into XL by I max into Z, as Z is R because at resonance, right, this denominator voltage at resonance means Z is equals to R. So Q is XL by R or XC by R. So Q is equals to XL is omega R into L, X is 1 by omega R C. Now here you can also define as it is the ratio of the inductive reactance to the impedance at resonance means R. That only, right? Capacitive reactance to the impedance at resonance. Capacitive reactance to the impedance at resonance. So Q is equals to omega omega R L by R, right? Here omega R can be written as 1 by root LC, right? Omega can be written as 1 by here omega can be written as 1 by root LC, right? 1 by root LC L by R. Here 1 by R square root of 1 by square root of L by C. This is Q. So, and you can also define as quality factor as a ratio of the inductive power to the applied power. Same, inductive voltage to the applied voltage. Inductive power to the applied power at resonance or capacitive power to the applied power at resonance. So capacitive voltage to the applied voltage at resonance means here if you multiply I on both sides, it will become power at. Then power at capacitive power to the applied power at resonance. In this way you can define. Or ratio of the reactive power to the applied power. Reactive power means that imaginary power, because that inductive power, capacitive power are imaginary powers, right? That's why ratio of reactive power to the applied power. And the relationship between quality factor and bandwidth. Here, first we got this one, right? Q is equal to 1 by root LC L by R. Take that. 1 by root LC is omega R, right? Okay. This one you can write as 1 by R by L, right? 1 by R by L is 1 by omega 2 minus omega 1, right? Here we got omega 2 minus omega 1 is R by L. Then L by R will be 1 by omega 2 minus omega 1. Omega R is 1 by root LC. Here we got omega R is 1 by root LC. That one. So this we can write as omega R by omega 2 minus omega 1. Omega R is 2 pi fr, omega 2 is 2 pi f2, omega 1 is 2 pi f1. f2 minus f1 delta f. So Q is the fr by delta f. So it is the ratio of the resonant frequency to the bandwidth. That's it. This we also learned in lab internal for LCR series circuit. That's it. Thank you. Bye bye.